Good morning, everybody.
Good morning.
Good morning. So today, we are going to cover Unit 4, Section 4.3, Logarithmic Properties. We're going to have a lot of formulas to study today. The focus is to understand. I'm going to prove those formulas. The process of proving is to help us to understand the formula. And at the same time, I hope you can memorize the formula and application. So today, our focus is to understand, memorize, and apply formulas related to logarithmic and exponential functions. All right. So number 10 here, we have 8 formulas to study. The first one is log with base b 1 equals 0. I hope you still remember the names of the 3 parts in a logarithmic function. B here is the base, right? B here is the base. 1 here is the argument. The 3 parts are base, argument, and log. Then 0 has to be the log. 0 is the value of the log, right? With base b and argument 1. And we are able to convert the equation in its exponential form. So its equivalent form in the exponential expression would be b to the power 0 equals 1. B is the base. Log, remember log, always on the shoulder, a piece of wood, right? Carrying on the shoulder. So b to the power 0 equals argument. Since b is the base of the log, b has to be bigger than 0 and not equal to 1. So a non-zero number to the power of 0 equals 1. This is an identity or a true statement we have covered in Foundation 2. Those two equations are equivalent. All right. So log with base b of 1 equals 0 is equivalent to b to the power of 0 equals 1. You might want to memorize. If we have a logarithmic expression whose argument is 1, then the value of the log is 0. You might want to remember that. If the argument of a log is 1, then the value of the log is 0. All right? So I explained the reason because those two expressions are equivalent. And b to the power of 0 equals 1 is a true statement. Any non-zero quantity is raised to the power of 0 gives 1. So that's the first formula. Now we need to memorize, okay? Whenever you see the argument of the log is 1, okay, 0. The value of the log is 0. Number 2. And allow me to erase those stuff, okay? I'm recording the class, so if you want a note, you can just take a screenshot from the video. Second equation, second formula, log with base b and b equals 1. This log has base b. Argument is also b. And log is 1. We can convert or rewrite that equation in its equivalent exponential form. Base b, base, right? Base b is raised to the power of 1 because 1 is the log. Log is a piece of wood, so it's on the shoulder, equals the argument, which is b. And this obviously is true statement, right? B to the power 1 to equals b. The first power of any base is just the base itself. It means the second equation, the second formula, is equivalent to b to the power 1 equals 1. Equals b, sorry. b to the power 1 equals b. And this formula is equivalent to b to the power first equals b. They are equivalent. Since b to the power 1 equals b is a true statement, so log with base b of b equals 1 is also a true statement. You can memorize this formula as if a log whose base and argument are identical, then the value of the log is 1. You're going to have to purposely memorize. That's the second equation, second formula. The third formula is log with base b and then b to the power of x equals x. Okay, this expression, this equation looks more complicated, right? But it is a log function. It's actually a log function, this equation. It should still contain the 3 parts. So let's identify the 3 parts. The important thing is the argument is not just the one single variable or number. The argument in this case itself is an exponential expression. I highlighted in yellow. So the yellow part as a whole is the argument of this expression. Okay, so b is the base. Argument, the yellow is the argument, okay? The whole thing, b to the power of x, the yellow part is the argument. You do not separate them. This is one whole thing. And the log is x. X is the log. Same idea. We are going to rewrite that equation in its equivalent exponential form. So base to the power log equals argument, right? So once we repeat the process so many times, you should be able to grasp the process. Base is b to the power of log, log is x, equals argument, which is b to the power of x. Isn't that an identity? The left side and the right side are identical. Of course, this equation is a true statement, right? You see that? So log with base b and then b to the power of x equals x. If you see something like that, if you see log with base b, b to the power of x, you know the value is going to be x. Yeah, figure out a way to memorize the result. Later, once we learn the power rule, we are going to go back number 3, and you would will make sense of number 3 in a different way. Okay, so here I proved number 3, the formula is correct, is a true statement. Okay, so it's equivalent to b to the power of x equals b to the power of x. So that's number 3. Let me erase those, and then we go to number 4. Number 4, b is raised to the power of log with base b, x. The formula says that expression equals x. So this equation, in what form? This equation actually is in the exponential form, all right? It's in the exponential form. We are going to see this part as one whole thing. I colored in green. Then in the exponential form, let's identify the 3 parts. B is the base. No problem to see that, right? And remember, whatever on the shoulder of the base is what? Is a piece of wood, right? remember the base always carry a piece of wood on the shoulder. So the green part, log with base b x, the green part is the log, okay, is the log. And of course, the other one would be the argument, because we only have 3 parts. If you found 2 of them, then the remaining one would be the third. So now we have our 3 parts, base, log, argument. With the 3 parts identified, let's convert the equation from the exponential form to its equivalent logarithmic form, okay? Log with base b, yeah, base is given, base is found as b. What's the argument? Argument is x, right? Equals what? Log. Log is the green. Log with base b, x. Left side, right side are identical. Of course, it is a true statement. Since the 2 equations are equivalent, if this is a true statement, then the original formula or equation is also a true statement, all right? So it is equivalent to, and I actually have those equivalent form found. The equivalent form is log with base bx equals log with base bx. Okay, so we're gonna put a star here in front of number 4. Means later we're gonna go back once we have more content learned, and we go back can make sense of the equation in a different way from a different perspective. All right. Do you guys have any questions so far? What do you think about it? The first 4 formulas. You just need to be familiar with those formulas. And then let me actually try to explain number 3, number 4 in this way to see if that helps, all right? Do you remember logarithmic function and the exponential function, they are inverse function. Means they cancel each other, all right? So for number 3, the expression on the left side, log with base b, b to the power of x, what we can understand is, you know, we give the input x, right? And let the input x go through an exponential function with base b, all right? Exponential function with base b. Then the middle product, remember I always use this, would be b to the power of x, right? And then we let the semi-product go through its inverse function, which is a log, also with base b, you know, also with base b. So then we would have log with base b and b to the power of x. Since this function and this function, they are inverse of each other, so they should cancel each other. So after the input x goes through the 2 functions, the input x should come out. Do you see what I'm trying to say? Yeah, let me do it again. I think this might help you to understand, at least maybe some of you. So let's say we know log b to the power of x and log with base b of x. Those 2 functions are inverse function, right, with the same base b. So suppose we have an input x. We let x go through 2 functions, and the 2 functions are inverse of each other. Since the 2 functions are inverse of each other, we should have x comes out because the 2 functions cancel each other, right? That's what the inverse means. So if we let x go through the exponential function b to the power of x, then the middle, then b to the power of x would come out from the machine, right? It's exponential function. And then go through the logarithmic function with base b. Then what will come out? What we'll have? We will have log with base b. And this is the input for the second machine. So we should have this. And you know what? That should be equal to x because the 2 functions are inverse of each other. Does that make any sense? Kind of. So when you have an input x, you use b to raise to the power of x. Actually, you are applying an exponential function. And then on top of that, you apply a logarithmic function. And the two functions are inverse of each other. So you go back x. Similarly, number 4 is the same idea. You have input x. You let x go through log function first. And you would have log with base bx. And then you're going to let that output from the first machine go inside the second machine, which is an exponential function. So you would have b to the power of log with base b of x. You're gonna put this on the shoulder of b to apply the exponential function with base b. And since those two machines are inverse of each other, this is supposed to be equals x. Start with x, apply log first, and apply exponential. Since the log and the exponential are inverse, and you should go back x. It's a different perspective to prove this formula. Any questions about the 4 formulas so far? Any questions? Or which part is not clear? I can repeat it.
No, I think I understand it pretty.
Okay. All right. Very good. And the next 3, number 5, number 6, number 7 is a set. Okay. And those three formulas are very important. So they have their names. The number 5 is called the product rule. Number 5 is called the product rule. Let me write a formula here. It says log with base b x plus log with base b y equals log with base b x times y. This equation, this formula is called the product rule. The product rule. The product is right here, okay? It's right here. Sometimes we use this formula from the left to the right. Sometimes we use the formula from the right to the left. If we have an addition of 2 log with the same base, based on this formula, we are able to rewrite the addition as 1 log, keep the base, and multiply the 2 arguments. So from left to the right, we use it when we need to condense. When we have an addition of 2 log with the same base, very important, the base have to be identical. Then we can condense this addition with 1 log. Keep the base, still is b, and the argument would be the multiplication of the original 2 arguments, x times y. Multiplication, product. And that's the reason the rule is called the product rule. And we are not going to prove those formulas. It's going to take a while, and in the past I did that. It doesn't really help students to learn. So you're going to have to figure out a way to memorize it. The more times you use it, the more times, the better you memorize it. And from the right to the left, sometimes we need to apply the same formula from right to the left. That's when we need to expand. Sometimes we need to expand. Suppose both x and y are positive. It's important because we have to make sure x is positive to make this log well-defined. Y is positive to make this log well-defined. We know argument has to be positive, right? Argument has to be positive. Let me stress that fact. Log with base b star. Star is the argument. Argument has to be positive, cannot be 0 or negative. All right. So if we have one log with base b and the argument has the structure of a product, okay, argument has the structure of product, then we are able to rewrite that log as the addition of two logs. The first factor in the product going to be the argument of the first logarithmic function, and the second factor y in the product is going to be the argument of the second log function. Okay, yeah. So in this topic, we only explain or try to make sense of the formula. Next problem, we are going to use them. All right. So this is number 5. Number 6 is called the quotient rule. The formula is log with base bx minus log with base by equals log with base bx over y. Okay. We also need to use this formula sometimes from left to the right. That's when we need to condense. Sometimes we use from right to the left. That's when we need to expand. When we need to condense and we see a difference of two logarithmic functions with the same base, then we can rewrite the subtraction, rewrite the difference as one single log. With the same base, keep the base b, and use the first argument as the numerator and the second argument as the denominator, and we make a quotient. And the quotient x over y is the argument of the condensed log. Quotient x over y is the name quotient rule comes from. That's from left to the right. If we need to subtract two logs with the same base, and the result is going to be one single log, and the argument is going to be x over y. From right to the left, sometimes we are required to expand a log. How do we use this rule to expand? We look at the argument. If the argument right here, if the argument has a quotient structure, like a numerator over denominator, then we can rewrite or expand that single log as a difference of two logs. Numerator goes as the argument of the first log. The denominator goes as the argument of the second log. Again, x, y have to be positive. Okay, everything in the argument has to be non-negative, cannot be zero either. So that's quotient rule. Number 7 is the power rule. Power rule. The formula is log with base b. Let's see, did I use a or alpha here? Yeah, I use r. Okay. X to the power of r equals r log with base b x. Okay, so this exponent in the argument can be taken out and put it in front of the remaining log. So that's when we need to expand. So this time from left to the right, we expand. If the argument I'm going to highlight in yellow, this is the argument, okay? If we have a single log whose argument has the structure of a power, the reason is called the power rule because the structure of the argument is a power or exponential expression, then we are able to move the exponent in the exponential expression in front of the logarithmic function. The r is gone, right? It's moved away. So on shoulder of x, there's nothing. So this is to expand. And if we do use the formula from right to the left, that is to condense. How do we condense? When we have a number times a log, then we can move that number on the shoulder of the argument. That's the condense. Yeah, those 3 formulas are very, very important. As I said, proving not necessarily will help you too much. So we would have to try to memorize exact what the 3 formulas are. There are some creative and looks similar formulas. They are incorrect. You're going to be very careful. Do not apply the 3 formulas incorrectly. Okay, next we are going to talk about number 8. Number 8 is about the change of base formula. It's very simple, okay? You don't have to worry about the formula, to be honest. Change of base formula. If you go to the calculator, you should only see common logarithmic function and natural logarithm function. We mentioned that last time, right? If you go to the calculator, any type of calculator, you do have logarithmic function, but you would only have either log, which means a log function with base 10. We call that common log. Or you will see ln, right? ln means log with base e. E is the Euler number, and we call that natural log. But what if you need to compute log with base 2 of 10? Then you go to the calculator. You cannot calculate it. You cannot evaluate this expression because you will not find a log function with base 2. Because the calculator only provides base 10 and base e. So in this case, the change of base formula gonna apply. Okay. So let's say we wanna calculate log with base 2 and 10, like what I had earlier. Then we can do this. We can use the change of base formula. We are going to write this log as a quotient of 2 logs with the same base. Any base would be fine, okay? Then we can use base 10. The common log, base 10. And the numerator, the argument of the numerator is going to be the argument of the original log. And the argument of the denominator is going to be the base of the original log. So you see what happened? So this number, this argument goes on the top. This base, we only have 2 numbers, right? Goes on the bottom. And the base here could be any base, to be honest. By the formula, it could be any base. But since our purpose to evaluate, we want to find the number, we should use either 10 or e, right? So it is, the numerator would become log 10. The denominator would be log 2. And then you go to the calculator. You would be able to find log 10 and then divide by log 2. Then you would have the value of the original log. So that's how do we use the change of base formula to evaluate a logarithmic function or expression. And you might wonder, could I use e or ln? Yes, that's actually what I do. So it really doesn't matter, it's the same thing, by the way. So log with base 2 and 10, we can also use natural logarithm to evaluate. So the numerator is going to be ln 10. The bottom is going to be ln 2. So as you can see, this number goes on the top, this number goes on the bottom. And then you go to the calculator, you can find the ln 10 and use that to divide by ln 2. And you will have the same result. Okay, I can actually, let me stop share of the note and I can share the calculator and quickly show you what's going on. This is log, this is a common log. The base actually is 10, even you don't see it. So you do log, common log 10, use that to divide by common log 2. That's the result. That's the value of log with base 2 of 10. If we use natural log, you will see the result is going to be the same. ln natural log 10 divided by natural log 2. We would always have to manually complete the parentheses the system, the calculator start the left-handed parentheses, start the parentheses, but we have to close. Same thing, right? It's the same thing. So change base of formula provide a method to calculate or evaluate any log expression, All right. So I actually would divided the 8 formulas into 3 categories. Number 1, number 4, you can see those as properties of a logarithmic function. And the 5, 6, 7, they are a set. 5, 6, 7, they are a set. And we use this set of formulas to expand and condense when we need it. And number 8 is by itself. The change of base formula is used to evaluate log functions or log expressions. All right, let's apply them. Every time we apply them, we should write the formula once. The more time you write it, the more familiar you will get it about the formula. Okay, let's see number. Yeah, the number might be wrong. So application of the previous, the formulas in the previous topic. Okay, let's see this one. Evaluate this expression. You might wonder, could I use the change of base formula? Yes, you could. But we don't need to, because we have better formulas to apply. Why? Because the base 2 and the argument 1/8 is somehow related. Because we are able to write 1/8 as a power of 2. Okay? We should be able to write the argument. Yeah. 1/8 is the argument, right? Base is 2. We can write the argument 1/8 as a power of 2. So we just play with it. How do we write 1/8 as power of 2? Denominator. Let's look at the denominator first. Denominator is 8. We all know 8 is 2/3, right? Sorry, 2 cubed. We all know 8 is 2 cubed. Then the denominator now is a power of 2. And what happened to 1 over? Yeah, I taught this in foundation 2. So if we use 1 over something, we actually are taking the reciprocal of the quantity. And we know taking reciprocal is equivalent to placing a -1 exponent. So we can write 1 over 2 to the power of 3 as 2 to the power of 3 to the power of -1, okay? If we place a -1 exponent on a quantity, the blue is the quantity, is equivalent to taking the reciprocal of the quantity. And then the other way around is the same. If we take the reciprocal of the quantity blue, is the same with we place a -1 exponent on the shoulder of the quantity. I hope you remember this. And then we use the power rule we learned from the foundation 2. We can rewrite this expression as 2 to the power of -3 because we have 2 exponents. The first exponent is 3. The second exponent is -1. So we keep the base 2 and multiply the 2 exponents. 3 times -1 is -3. And that's how do we rewrite the argument 1/8 as 2 to the power of -3. All right, nothing new. You're supposed to be able to do that in the prerequisite course. And now we're gonna rewrite the argument as, we keep the base 2. Argument right now is 2 to the power of -3, right? Yeah, we notice the argument could be written as a power of 2, which is the base. 2 is the base. And we did it. The argument right now is 2 to the power of -3, okay? Could we move the -3, which is the exponent in the argument, in front of the log? And what's that formula? That's the formula we learned just now, is called the power rule. I'm going to write the power rule again. Log with base b x to the power r equals r times log with base b x. yes, if the argument of a log has a structural power and the exponent is r, we can move the exponent in front of the log. So the yellow argument is an exponential expression. The exponent is -3. So by the power rule, we can move the exponent -3 in front of the log. -3 log 2. So far so good? And anybody can tell me what is the log 2? What's the value of the logarithm expression with base 2 and the argument is also 2? Base and argument are identical.
1.
Yes, very good. We learned that formula. I think that's the second formula, right? Log with base b of b is 1 because it's equivalent to b to the power 1 equals b, right? When we have a log whose base and argument are identical, the value of the log is 1. So -3 times 1 is -3. So the answer here is -3. You might wonder, would that be easier if I just use the change of base formula? Yeah, it might be. But the purpose of this problem is to apply the formulas without using calculator. Questions?
No. You're
Okay.
understanding it right. You're explaining it really well.
Appreciate that. The second expression, a little bit small. I'm gonna rewrite it. With base log with base 3, the argument. What is that? I think it's 1/4. Let me see. Yes. The argument is 3 to the power 1/4. Let me yellow the argument. The argument has the structure of an exponential expression. When you see an argument whose structure is an exponential expression, you should think about the power rule. You should think about the power rule. Power rule says the exponent in the argument can be taken out and put in front of the log, right? Something looks similar, right, with the earlier. And once we put 1/4 in front of the log, and the log becomes log with base 3, and the argument also 3. We know when the base and the argument are identical, the logarithm equals 1. So we have 1/4 times 1, which is 1/4. So the result is 1/4. In Lumen, we don't really have a lot of problems. We're supposed to practice more than just 20-ish problems for each section. We should practice more. But the Lumen system does have the option for you to get a similar problem, different number. You should try that. Even you already have that problem correct, but you can try more times just to reinforce your understanding there. Number 3, the expression is a log. What's the base, guys? Do you see the base?
It's 10.
Yes, we don't see it because it's a common log. It's defaulted as 10, okay? And this whole thing, the whole thing is the argument, okay? Base is 10. The argument, actually is also closely related to 10. We are able to rewrite the argument as a power of 10. So the argument is right now is 1/10 million, right? 1, 1, 2, 3, 1, 2, 3. And that is 1/10 to the power of 7. 10 million, 7 zeros. So the denominator is 10 to the power of 7. And this, remember, 1 over a quantity is taking the reciprocal of the quantity, is the same with put a -1 exponent on the shoulder of the quantity. The quantity, the green to the power of -1, is the same with taking the reciprocal of the green. And we use the power rule, keep it 10, and 7 times 91 is 97. You should be able to write the argument, something like that, in that form. So 10 to the power 97, all right? And this time, right now, look at the argument again. The argument is a power. The argument is an exponential expression, is a power rule. We are able to move the exponent in front of the log to have 97 times log with base 10 and 10. This actually is log 10, right? It's just 1. Yeah, if you see log 10 or log with base 10 and 10, it is just 1 because the base and the argument are identical. So 97 times 1 is 97. The result of this problem is 97. Next. Evaluate each of the following without using a calculator. Of course, if you are allowed to use a calculator, you can always use the base of change of base formula. But we are not going to use a calculator. So we are using the formulas we have covered earlier. Let's get started. I'm going to label them. This is number 1, 2, 3, 4, 5, 6, 7. Okay. I think that's 1 over 5 as well. Okay. What's the value of the first expression? It is a log. Base is 1/5. Argument is also 1/5. What's the value of a log when the base and the argument are identical?
1.
Yeah, awesome, exactly. That one is easy, right? That one is straightforward. Number 2, a little bit tricky. We have different way to get it done. Log with base 1/4 and 16. One way to get it done is rewrite the argument as the power of the base. Yeah, how do we do that? That might be a little bit challenging because it involves some algebra, right? 16 can be written as the reciprocal of 1 over 16, right? 16 can be written as reciprocal of 1 over 16, or 1 over 16 to the power of 91. Do you see that? And 1 over 16 is 1 over 4 to the power of 2. So we can actually write 16 as 1 over 4 to the power of 92. If you know how to do that, that is one way to get it done. And now we can move the exponent in front of the log. And we have log with base 4 and 1/4. And since this log has base and argument identical, so the value is 1. So the answer is 92. All right. One strategy to evaluate a log, especially when the base and argument somehow related, then we should try to use this strategy. It is to write the argument as a power of the base. If we can write the argument as a power of the base, then we can evaluate. But this might be a little bit challenging, so we can do something else, right? We can try something else. We can try the method we learned from last time. We can let this be x and then solve for x. We can convert this expression. The equation right now is in a logarithmic form. We can rewrite the equation in the exponential form. The base is 1/4. Argument is 16. Log is x. So to convert, we're going to raise the base to the power of log equals the argument 16, right? And we can write 1 over 4 as 4 to the power of 91. And then we can write the left side as 4 to the power of negative x, and the right side as 4 to the power of 2, because 16 is 4 to the power of 2. Since look at the left side and the right side, they have the same base, right? We can cancel them, and we would have negative x equals 2. When we have negative x equals 2, we have x equals negative 2. And same result. You pick the method that you feel more comfortable. I gave you the time to take a screenshot. So far, so good? Okay, very good. Thank you. All right, so next, number 3. LOG with base 81, argument 9. Obviously, 9 and 81 are closely related because we know 81 is the power of 9, is the square of 9, right? And but we want to write the argument as the power of the base. The base is bigger right now. Could we write 9 as the square root of 81? You do need to have a good algebraic foundation in order to figure that out. 9 can be written as the square root of 81, right? Obviously. Rule 81 is 9, the principal square root. And we can also write the square root of 81 as 81 to the power half. Right? Square root of 81 can be written as 81 to the power half. And by the power rule, since the argument right now is a power, we can move the exponent in front of the log. Half log with base 81 and 81. And this is 1 because the base and argument are identical. So the result is 1/2. The result is 1/2. All right, result is 1/2. Number 4, could you help me to figure number 4 out? What's the result or the value of number 4? Log with base 3, argument is -1. Nobody wanna, what do you think? Log with base 3, -1. We don't need to use any formula, by the way. Do you notice something wrong? Log with base 3, argument is -1. Guys, could the argument be negative number?
No.
No. -1 cannot be argument, okay? Does not exist. You do not need to evaluate because it cannot be evaluated. The value does not exist, is not well defined. So we don't have to apply any formulas. I hope you recognize that. Very important, argument can never be negative, cannot be 0 either. Argument has to be positive. Argument has to be positive. Okay, number 5. Number 5 is actually simple. I need to stop to say easy or simple. Number 5 is straightforward. Could you work on it and let me know the result? Number 5, log with base 981. Yeah, what's the result? Base is 9, argument is 81. Any method that you'd like to apply? Basically, we have 2 methods. The first method, you can let the expression be x and then convert it to exponential form and then figure x out. The other method is to rewrite the argument as a power of the base. So what do you think? What's the value supposed to be?
2.
Yes, 2. Awesome. Very good. Okay, I'm going to quickly show you. So if we use the first method, let LOG with base 9 of 81 is x, then we can convert the expression, the equation, to the exponential form. Base to the power log equals argument. And we know 81 is 9 squared. So as you can see, 9 to the power x equals 9 to the power 2. Those two quantities has to be the same. Similarly, another method, if we rewrite the argument as a power of the base, 9 to the power second, then we can use the power rule to move the exponent in front of the log. Then we would have 2 log with base 9, 9, and this is a 1. When the base and the argument are identical, is 1, so equals 2. So either way, both methods, you can try both to see which one you feel more comfortable. Number 6, you help me out. Number 6, what's the value of number 6?
0.
0, exactly. Okay. You know, number 6, we can also explain the result by using the formula we learned earlier. You know, log with base 1/7 of 1. We actually could write 1. 1 has millions, many unlimited ways to of transformation. In this case, we can write 1 as 1/7 to the power of 0. Then we use the power rule. We move the 0 in front of the log. Then we have a 0 times log with base 1/7, 1/7. You know, it doesn't matter. This is 1, we know. But even other, it doesn't matter because 0 times that number is 0, right? And also, the first formula we proved today, the very beginning of the class, says if we have a log whose argument is 1, then the value of the log is 0. Okay, because when you raise this base, only when you raise the base to the power of 0, you have an argument. You have the argument 1, the exponentiation expression 1/7 to the power of 0 to the equals 1. Number 7. Would you be comfortable to try that? The base is 10. The argument is 1/10. Could we write 1/10 as the power of the base? Could we rewrite the argument as a power of the base? 1/10. Well, I have covered that, right? 1/10 is a reciprocal of 10. It's actually 10 to the power of -1, right? And then powers. We have -1 times log with base 10 and 10. This is 1, so -1. Result is -1. And done. We're through this problem without using a calculator. Any questions?
No, I understand it.
Okay, thank you. Next problem is about expanding and condensing. Okay, this one, we are given a single log. Base is 10. We don't see it. That means default as 10 is a common log. The argument is very complicated, right? In the parentheses, the whole thing, that's the argument. You know, pretty crowded, very busy. And we need to write the following expression as a sum or difference of logarithms with no exponents. So this means to expand. If you see the requirement like that, is actually ask us to expand as much as possible. Okay, let's do it. log with base 10. Log with base 10 and has the argument, the structure of the argument. You know, I'm going to talk about structure, the importance of structure again. Very important. Just like when you are a physician, it's important to see the structure of the human body. When you are architect, it's important to see the structure of the buildings, right? Now we are learning mathematics, algebra. It's important to see the structure of the expression. The bigger structure of this argument is a quotient. Z squared, okay, is a quotient. Numerator is blue. Denominator, so yellow. So the bigger structure of the argument has a structure of quotient, is a quotient, blue over yellow. Because the structure of the argument is a quotient, we are going to apply the quotient rule. Let me write the quotient rule for you. Log with base b, x over y. That x and y is different from the xy in the problem, okay? Equals log with base bx minus log with base by. So by using that quotient rule, we could rewrite the log here as a subtraction. Quotient rule, when we expand, we get a subtraction or difference of two logs. The first log has the blue as argument. The second log has the yellow as the argument. All right, this step, we applied the quotient rule. Since the argument is a quotient, blue over yellow, so we could rewrite that log as a difference of two logs, log blue minus log yellow. But we are not through yet. The expansion is not thorough yet. We have to keep going. Because we notice the blue, this log, yeah, I'm gonna rewrite it, okay? I'm gonna rewrite the color as, I'm gonna use the two different colors. How about pink and purple? A little bit similar color. And yeah, for that log, the argument, it was the original blue, has the structure of a product, okay, a product, minus log with base 10 and z squared. I'm gonna keep that for now. Keep that for now. Okay, so now since this log, whose argument is a product, since this log in the box, whose argument is a product, we are going to apply the product. We're going to apply the product. Let me write a formula here. Product rule. Log with base b x times y equals log with base b x plus log with base b y. When the argument is a product, we can expand that log as an addition of two logs. So here we are going to write that as log with base 10 pink plus log with base 10 purple. I hope the color scheme help you to understand. It doesn't mean to make you feel, confused. I think the color should be able to help, at least help me to explain. So what we have done in this step, is to apply the product rule to expand this log, log pink times purple, as log pink plus log purple, all right? So, but we are not through yet, still not through yet. It says, with no exponents. So now the last step, we are going to get rid of the exponents. In the all the three log in this expression, in this step, the arguments have a structure of a power. Since the argument has structure power, we are going to use a power rule. This is a very good problem because we use all the three formulas. Log with base b x power r equals r log with base b x. Means the exponent in the argument can be taken out in front and put in front of the log. So we're going to do that. We're going to put this 17 in front, this 19 in front, this 2 in front, and then we would have 17 common logarithm with of x plus 19 common logarithm of y minus 2 common logarithm z, and that's the final answer. It's a good question. It uses all the three formulas. Questions?
No.
No.
Okay. Next. Same thing. I'm gonna have more room for that solution. Use the laws of logarithms to rewrite the expression. Okay, this is to expand as well. This is to expand as well. Expanding. Ln means log with base e, so it's a natural logarithm function. So let's look at the structure of the argument. We have an x to the power of 12, square root x minus 1, all over 3x minus 15. Look at the structure. Analyze the structure of the argument. Numerator is blue, denominator is yellow. The structure of the argument is a quotient, blue over yellow. The bigger structure is a quotient, blue over yellow. So we are going to apply the quotient rule. Quotient rule can expand or rewrite this log as a difference of two logs. The first one is the blue, the numerator. So we have x 12 power square root x minus 1 minus log, not log, ln, natural log of yellow, 3x minus 15. First step, we applied the quotient rule. Oh, that's supposed to be blue. Ln blue over yellow equals ln blue minus ln yellow. Okay, that's the step. Next, we are going to rewrite the blue argument. We can write that as x to the power 12 times x minus 1 to the power half. And I'm going to label color them. This is pink and this is a purple. And look at the purple, guys. Square root of x minus 1. Square root is a radical. And if we rewrite a radical expression to its equivalent exponential expression, we have the power 1 over 2. So the blue argument now is a product. It is a product. And I wrote it as pink times purple. Pink times purple. All right? And the minus ln I think the yellow is pretty simple already. It really depends on the requirement of the problem. I think this is good enough. I'm gonna keep that like that. Use the laws of logarithms to rewrite the expression. It doesn't have much specific requirement. Okay, so next step, I'm going to apply the product rule because this log whose argument is a product. So we are going to use the product rule to expand it. And we're going to have a ln natural log pink plus natural log of the purple. And bring down the last log. Okay, almost there. The pink is a power, so we can use the power rule to move the exponent in front of the log. The purple is also a power, so we can move the exponent half in front of the log. And the result could be 12 ln x plus half ln parentheses x minus 1 minus ln 3x minus 15. Yeah, about the yellow part, about this part, I can elaborate just my concern, okay? I think it doesn't matter. So that part in the red box, if we really want to go very thorough, we can rewrite the yellow 3x minus 15. We can factor that yellow. Factor that yellow as 3 times x minus 5. And then the argument becomes a product. So we can apply the product rule, ln 3 plus ln x minus 5. So that's my thinking. So if the question requires to do that, then the final answer should be 12 ln x plus half ln x minus 1, and then minus ln 3, and then minus ln x minus 5. Because this part should have a parenthesis, and then minus the parenthesis, when we apply the distributive property, we should have a minus here. All right. And this definitely is very thorough. There's nothing we can do further. Okay, so this is expanding. We did 2 problems about expanding. See, the next problem is condensing. Next one is condensing. The given expression has a multiple log. Good news is they have the same base. Okay, so we are going to condense them. And I see 3 parts in the expression. 3 log with base 2, argument 2x plus 1. The second part, minus 2 times log with base 2, argument 2x minus 1. And the plus 2. 2 here looks very lonely. It's not even a log. But we may rewrite 2 as a log. Could we write 2 as log with base 2 of 4? Could we write 2 as log with base 2 of 4 with argument 4? Same value, okay? Yeah, you figured out. 2 is the same with log with base 2 of 4. And this way, all the 3 parts in the expression are log with base 2, same base. Okay, and then what do? We are going to apply the power rule to put a coefficient in front of the logs back inside the argument. So these 3 are going to go on the shoulder of the parentheses, go on the shoulder of the argument here. And these 2 And you don't want to do -2. You're going to keep the subtraction sign and only put a 2 back on the shoulder of the argument. And that one keep the same. So let's do that. So this step, we're applying the power rule to, get rid of the coefficient in front of the log to condense. LOG with base 2, argument 2x plus 1 to the power of 3, minus LOG with base 2, argument 2x minus 1 to the power of 2, and then plus LOG with base 2, 4. Okay? And these two, subtraction, we can use the quotient rule to condense as 1. Okay, to condense as 1. Let me write the quotient rule again, because this time we are using a different direction, right? So LOG with base b x minus LOG with base b y equals LOG with base b x over y. This time we are going from the right to the left. No, sorry. Go from left to the right. From left to the right. So we are going to rewrite. If the color helps, I will do the color. So this is the argument of this, the first one. This is the argument of the second one. So we are going to condense the subtraction, the difference, as 1 log with base 2. And the argument is going to be blue over yellow. Blue over yellow. Don't forget, we have a LOG with base 2 of 4. And next step, we are going to condense by using product rule. Product rule says LOG with base bx plus LOG with base by equals LOG with base bx times y. So this argument gonna multiply this argument as the new argument of the result. So we're gonna keep the base LOG with base 2, and we're gonna multiply the two argument, okay, because the product rule multiply. And we're going to have 4 on the top, 2x plus 1 to the power of 3 over 2x minus 1 to the power of 2. And this is the final answer. That is one single log. We condensed it. It is the same with the original given expression, but form-wise is one single log. So that's the condensing. That is the condensing. Let's practice more about condensing. The next problem, write as a single logarithm, express coefficients as powers inside our logarithm. So it means apply the power rule. And this one actually is simpler than the previous problem. And we are going to do the power rule first. And then we have ln x cubed plus ln y to the power of 9th minus ln z to the power of 6. Product rule can write this addition as one single log with an argument that is the product of the original two arguments. So this one, the blue argument times the yellow argument gives the new argument of the log, and minus ln z6. Now we're going to do quotient rule, right? Because we have a difference with the same base. We do quotient rule. So this time, this is going to be the numerator, this is going to be the denominator in the argument. So x cubed y to the power 9 over z to the power 6. And that's the final answer. That's the final answer. Okay. Number 9, LOG with base 3 of 24. This is to evaluate. This is to apply the base of change of base formula. This is to apply change of base formula. So log with base 3, 24. Couldn't we use the formulas? Probably not, because the argument is 24, the base is 3. I don't see the argument as a power of the base. So we would have to use the change of base formula. So we can write that as log common log 24 over common log 3. Use a calculator. Or we can use natural log 24 over natural log 3. And we would have the value. I shown you earlier for a different problem. This would be similar. I believe you know how to get it done. Use a calculator. So this is very not very challenging. Just use the change of base formula. Knowing the argument gonna go on the top, the base is gonna go on the bottom. Okay, that's everything for today. Next section is to solve exponential equations and logarithmic equations, but that's section 4.4. Today's 4.3 mainly are about the formulas. Yeah, mainly are about the formulas. The formulas, I put them together. Here. I put them together here. And I think, you know, if you can get a good score for this chapter, in a sense, depends on if you are familiar with those formulas. If you know when and how to apply those formulas. All right, guys. We have 3 minutes. I'm gonna do the attendance for today. We have 5 participants. Kaida, Eliza, Michael, Ether, Max. Max, Mike. Okay. All right, guys. Thank you guys for coming. Feel free to email me if you have any questions. Do you have any question now? Then I'll see you on Tuesday.
See you Tuesday. Thank
Okay.
you.
Good. See you Tuesday.
See you
So for
Tuesday.
coming.
Bye.
Have a good weekend.
Yeah, bye-bye.
Yeah, Professor.
Hi, sir.
Hi, good morning. Yeah, okay.
Stop the recording. Okay, yes.
Yeah, I have a question I didn't want to ask when the class was there. I'm just curious and anxious